Hello, everybody. Welcome. Yep. Hope everybody had a nice weekend. Anyone do anything fun? Yeah. Pandemic life, huh? Went for a car ride. That's pretty exciting. Okay. Well, hopefully this will brighten up your week then. So the plan for today is to keep going on with our proof practice. So we're going to work on worksheet 4. Last time we did kind of one proof together, and then you guys worked on one briefly at the end of class. So I want to spend a bit more time today going through some together, giving you a chance to work through some with your classmates. And then we'll start towards the end of class just talking about some ideas from sets. And then your reading assignment for Wednesday is going to be set operations, union, intersection, that kind of stuff, just to make sure you read up on that before we come to class. And then on Wednesday, we'll start doing some proofs with sets. So homeworks are up online. For this week, it is due again on Thursday. So hopefully you can get started on that a little bit. And then it's basically a bunch of questions about statements, negating statements, quantifiers, that stuff we've gone through. And then you have 3 proofs to work on as well at the end. So if you had some trouble with those, hopefully what we talk about today will help with that. Any questions about the course or anything else? Hopefully you're kind of getting into the flow, the workflow of things, like there's a quiz before class, got longer homeworks due once a week. That's the plan. Okay, so if there aren't any questions, then let's jump back into where we were last time. So we did 2 of them together, or at least we did the first one together, and then you guys worked on the second theorem over here towards the end of class, where we worked with the conditional statement: if x is odd, then x squared is odd. And so just to back up and talk in general about how direct proof works. So when we are doing direct proof for a conditional statement, like if P, then Q, then how direct proof works is we start by assuming the hypothesis is true P, and then we try to work through some logical connections, and then wind up at the end showing that the conclusion Q therefore must follow. And that's what a direct proof would be. Any general questions about that? And so I think really the main definitions that we were working with in this worksheet are notions of even, odd, and parity. So one thing that I might suggest to you all is, as we're going through this semester, anything that we prove, you're allowed to use in subsequent proofs. So for example, we just proved that if x is odd, then x squared is odd. If you ever want to use this fact in a proof, you don't need to reprove this again. So it is fair game to go back and use statements as long as we've proven them together. So I'll just say, as you're kind of going through each of these worksheets, it might be useful to just keep a list of running definitions and kind of useful facts. Some of these proofs might not ever be useful again. Some of them might. Certainly the definitions are good to keep a tally of. So you might just want to have a sheet handy someplace where, every time we talk about a definition in class, you've got it someplace handy to refer to. So far on this worksheet, the main definitions again would be just being clear what it means to be even. If something is even, what does that mean? If I want to show something is even, what do I need to prove? That's the idea there. And the same for odd functions, and then this notion of parity. So these were the 3 main definitions that we're going to use on these proofs today. Okay, so let's give question number 3 a shot. That's a good place to start since we haven't done that one yet. Okay, that didn't help. I missed that. Okay, let me get rid of this. So when we're doing these proofs, it's helpful first to write out what the statement is, or copy and paste it. So in 3, what was the one we were trying to prove here? Just lost it. If anyone's, what do we have? If x is even, if and only if x plus 4y is even. Okay. What was it? 4x plus y. My memory is
X plus 4y.
fading today. Just started. X plus 4y is even. Okay, certainly it helps to have the claim that you're trying to prove written out before the proof. Okay, and now we want to do a proof of this. So we usually start our proof with indicating here's a proof. And so in this statement, we have a biconditional statement, right? So we need to be careful with biconditional statements. When we see if and only if, this means we have to prove 2 things for the price of 1 here. So this is saying that we need to show if P, then Q, and we also need to show if Q, then P. So this implication goes both ways when we see an if and only if. So this is something we haven't encountered before, but right, we're not going to change anything. It's just we need to do 2 direct proofs here. And so when we're doing a biconditional statement, it is going to be really nice to indicate to the reader which direction you're proving and which part of the proof. So this is kind of a general comment over here. Okay, which is if we're proving a biconditional statement, okay, tell the reader which way you're doing this. And by this stuff over here, I mean indicating over here that I'm proving P then Q. So this means in this statement, right, we're going to start by supposing P if we're going to do this with direct proof and then hopefully get to statement Q. So let's just kind of start then with by direct proof, we're going to suppose that statement P is true. Okay, and so when we're talking about numbers being even or odd, we're only considering integers here, but that was stated in the original claim too. So we're going to suppose that x is an even integer. And if you're trying to keep track of what the goal here is, right, the end of at least that direction of the proof would be therefore, right, Q is true, x plus 4y is even. So if you're ever having trouble with these proofs, I do think it might be helpful just to say, okay, if I'm doing this by direct proof, what would my first line be? What would my last line be? What am I assuming? What am I trying to prove? Okay, so if x is an even integer, now let's use the definition of even integer, right? I'll just write that out in blue. So this would tell us that there exists some other integer call it anything we want other than X and Y. So that we get just essentially by rewriting the definition of what it means that X is even. Okay, these little comments that I'm putting up here are just little annotations. Like you wouldn't want to include that in your proof, but in case you're curious where that came from. Okay, questions? And so now, we're hoping to show this. And therefore, if we want to show that X plus 4Y is even, let me just do some scratch work over here. Right? We want to show that that is equal to 2 times an integer in order to show that X plus 4Y is even. Okay, and so somewhere along the way, anytime you introduce a new letter or some new notation, you should tell the reader what that notation is representing. So I did that here, right, when I introduced X. I did that here when I introduced A. I'm going to do that here when I introduce Y. Just so the reader knows, okay, Y is an integer. It's not a function. It's not a set. It's not some other thing. Okay, so okay, now I'm just going to I want to say something about this X plus 4Y. Hopefully it equals 2 times something. So let's use the previous bit of logic that was in blue, that X is equal to 2A because X is even. I kind of ran out of space here, but okay, I'm just going to factor 2 out from the right side of the previous expression, previous equation. Okay, and so now what I've shown is this expression X plus 4Y can be written as 2 times a quantity, which is an integer. Let me just kind of get this out of the way. So what we've shown here is this quantity over here. This is what we're calling B. And we just need to be really clear to the reader that why did we pull out the 2 is because now we can write it as 2 times an integer. And that by definition means that this thing is even. So there's nothing else I need to say over here, because once I've shown that X plus 4Y is equal to 2 times an integer, that proves that it's even. Any questions? And now is not the time for celebration, though no one seems particularly happy that we've just proven something. I'm sure that that's why your screens are blackened out, to hide your relief, but we're not quite done, right? Because again, this was a biconditional statement. So be really careful. We need to prove two directions here. So we've done one direction, and now we would indicate that we're starting on the other direction. Okay, and now we indicate we're proving Q implies P by showing the arrow going in the other direction. And again, these are really not optional things to do. These being indicating what direction you're going. This is really helpful to the reader to know which way you're handling things. And in fact, you don't need to, you could have done this one first and then that one second, but it is important to tell the reader which direction you're proving. So then if we're going in the other direction, we're going to start by supposing that Q is true. So now we're going to start with Q. And we're trying to show P. So it's reverse now. Any thoughts, suggestions about what we could do here?
So I started by saying, suppose x plus 4y is even. And then I set x plus 4y equal to.
What do you think a good next sentence would be for this proof?
I would write that, don't we know that x is even? Yeah. Oh, sorry, therefore x is even. Oh, wouldn't you want to rewrite this as a form of like 2x?
Okay, so just to full disclosure here, I just randomly generated a list of your names. So I'm not trying to put anybody on the spot. You'll all get your chance to be on the spot. I just like hearing from different people in the class. So yeah, I do see there's a chat in here, so I'll take those, but just be aware, if I do happen to call on you, not picking on anybody. Yeah, so we've got that. Suppose the x plus 4y is even. Oh, do I not have my microphone turned on? That's very, very possible. No, this here. Did someone say something? Sorry, I missed it if you did. That's a no. I can't hear anything, so I don't know if anyone's talking. I'm gonna guess. Someone want to say something? I just want to see if I can actually hear you.
Can you hear me talking?
I do, yes. Okay. Thank you, Mitchell. Okay, that's weird. Sorry, I missed I guess I might have been on mute. Someone want to share again? Sorry if you did.
Since x plus 4y is, we stated even, can't we write it as x plus 4y is equal to 2a?
Yeah.
Or it must be divisible by 2? Because
that's
it's
right. Thank you. That's right. So let's kind of start with where we did before. Like, okay, suppose x plus 4y is even. By definition, what does that tell us about this expression? So based on that previous sentence, I can't jump too far ahead, but the next kind of logical connection would be, okay, well then there exists an integer. We could call it whatever we want other than x and y. Okay, and again, we just want to be really careful that each sentence shouldn't take a whole lot of thought from the reader to move on to the next sentence. So, okay, that's even. Yeah, I see why x plus 4y would therefore have to be 2a. Good, thank you. And then I see Diane had a suggestion about, well, let's now factor the 2 out from, let's see, sorry, 2x plus 4y. So we'd like to show that this is going to equal 2 times b, right? In order to get this concluded here. So now I've got this expression over here. I would like to say something about x being equal to 2 times something. So what might be a good thing to try here? Let's see. So you got any thoughts, Keenan?
Um,
So we've
would
got,
we?
like, we're at this point, and I'd like to get to this point. So what can I do to this equation over here to start to move it towards this direction where we've got x is equal to something?
Would we put 2b in for x and then factor like before or no?
So can I substitute x with 2b? That's a very good question. And I see that some people are suggesting that in the chat as well.
I think so.
So do we know that x is equal to 2b at this point in the proof?
No.
Not yet, right? So be careful. This happens a lot, is like, okay, we kind of get crossed up with what it is that we're trying to show and assuming that is true. So yeah, we want to show this, but we don't know it's true yet. So some of you are maybe starting to think about maybe some other proof techniques, like let me just plug in the thing that we're trying to show and see what happens. But with a direct proof, that should be just the very last thing that we get to. Yeah, and so there's a couple of suggestions about moving the 4y to the other side. Yeah, so I think that's like a really good idea to think about. Well, I know that x should be 2b somewhere along the way. Where do I fit that in? And this is a really big caution that shouldn't come in until the very, very end. So now let me take this expression, and if you want to, be very explicit, that would give us x is equal to 2a minus 4y. I don't think you need to say subtracting 4y from both sides. I think that part would be pretty clear to the reader, but if you want to be really explicit, you could say that. You could just as well just say, this gives x equals 2a minus 4y, and I think the reader would see where that came from. Okay, but again, if you're kind of thinking about how much detail do I need in here, think about trying to explain this to a classmate and trying to be detailed enough that the classmate wouldn't have too many questions about what you were doing. Okay, and so now we've got the 4y moved to the other side. We would like to get to the point where we can show that x is equal to 2 times some integer. We're just about there, right? So now that I've moved the 4y to the other side, then I can write that x is equal, I can pull out a 2 from each of those terms. That's not how I would do it, though. So that would give me 2 times the quantity a minus 2y. So that gives us 2b. That gives us 2 times an integer, I should say. And I did kind of leave out a detail here, like, well, how do we know that a minus 2y is an integer? Well, if a and y are integers, that would be true. So we don't need to really justify that. I think we all are pretty comfortable with that part. But I do just wanted to make a comment that this stuff over here is an integer. And so that's why x is now of the form 2 times integer. And that completes the other half of the proof now that we've shown this piece right there. Great, thanks for these comments. It's great. Sorry, I had my mic off. I'll leave you guys alone, or my speakers off. All right, any questions about that? If you don't put a red box, is it okay? That's fine. I'll just say that's like the most exciting part of a proof. It does kind of indicate like to the reader, done. I mean, if I'm grading this and I see that this was question 2, and then I see number 3 on your paper, that's also an indication that you're done with question 2. But that is a convention that you see a lot in textbooks as well. They'll put the little colored box at the end of their proof. Yeah, that's the least of my concerns right now. Yeah, if you're not putting those red boxes there, that's okay. Okay, so maybe we'll try doing another one together, and then that'll end kind of like us stretching, and then it's going to be time for you guys to warm up now and try some on your own. Yeah, let's take a look at the 4th one. Then we'll kind of take these in order. Some of them might follow pretty similar to some that we've done already, and I might just kind of skip some if I feel like you guys picked up on it. But this one's going to be a little bit different than the previous cases, previous examples. Okay. So we want to show that if x and y are integers that have the same parity, then x plus y is even. And we're going to, again, our only proof technique that's available to us now is direct proof. Right, so that's kind of the outline here. And let me just say, you know, as you're working on things like on an exam, it's always good to kind of, if you get stuck, at least start here. And if you are unable to fill in some of the details, you'll definitely get credit for knowing at least how this is how direct proof goes. I should start here and I want to end here. Okay. And so now let's think about what this tells us, right? So if x and y have the same parity, then we know that they're both even or they're both odd. And the tricky part here is that the proofs are going to go a little bit differently, possibly, depending on whether the case is they're both even or they're both odd. So here is a really good example for sort of a general proof technique. Let me just say, okay, using cases here. So we're going to break this down into 2 different cases. If they're both even, how does that proof go? If they're both odd, what would that look like? And I'll just say, like, when you can avoid using cases, it's best. But sometimes, you know, this is the most efficient way to do things. So, you know, it never hurts to try cases, and then you might want to look at your proof and see, did I really need two different cases, or could I have summed this up all at once? So let's see what it looks like here. So let's say when we're doing cases, okay, you should indicate to the reader, I'm doing cases, and for each case you number it. So case 1 here would be X and Y are both even. And then there's another case that we might have to consider, which is what happens if X and Y are both odd. That exhausts all the possibilities, right? There might be 3, 4 cases that you need to consider in some proofs. I would say at some point, if you get to a proof where you're considering like 10 different cases, that might not be the best way to do it. But if you've got 2 or 3 or maybe just 4 cases, this might be not too bad. So if X and Y are both even, so that's kind of handling one situation for the hypothesis, which is they have the same parity. So if they're both even, then we know X can be written as 2 times an integer, Y can be written as 2 times some other integer, right? And I want to make sure that X and Y are probably, in general, different integers. So these integers over here should have different letters too. Any questions? Okay, so we want to say something about X plus Y. Okay, sorry. So I was trying to clear some space here. So, okay, we've got X equals 2A, Y equals 2B. We want to show that X plus Y is even. So that's why I then thought about, well, let's consider what happens now if I add these two together. Okay, where A plus B is an integer. And we'll call that C. That handles the first case. Questions?
If you just said C is the element of like all integers instead of A plus B equals C is the element of all integers, is that fine, or do you have to do that?
Yeah, that's fine. You can just say C because, you know, I think for most readers at this point, they would see that, well, what is C? Well, C is this A plus B. Yeah, so I think,
Sweet.
yeah. So I'm trying to be really careful here about like using some notation, but not a lot. And I think that's a good thing here. Like I think putting this symbol Z instead of writing out integers is very common. And I don't think that confuses things too much. It actually makes it a little bit easier to read. So you just want to think about, does me using notation make this easier to read or does it make it harder to read? And I think if it makes it more difficult to read, then don't do it. Just write out the words. Okay, so now if we're gonna assume X and Y are both odd integers, basically the proof is gonna follow very similarly. I'm gonna even just like copy this. And let me just kind of read in what we need to update here. So now we're going to assume X and Y are both odd. Then we know that X is going to equal 2A plus 1, and Y is going to equal 2B plus 1. Oops. Get rid of this since this ending will be different. And that's why we kind of needed to handle this in two different cases. So, okay, we changed them to odd. Now we know that we've got these plus ones over here. So now when I take X plus Y, right, we're going to get 2A plus 1 plus 2B plus 1, which is equal to 2A plus 2B plus 2. So we have a little bit of extra stuff over here. We have this 2. We didn't have it over here, right? But that's not a problem because that's still, going to put this into the shape where it's 2 times some integer. And did I? Yes, thank you. Great. So see, I'm just catching up with the questions here. So some are going to me and some are going to everybody. What I don't know, I'm guessing the messages that come to me, Lindsay is not able to see. Yeah, so yeah, you're welcome to just send them to me. Just keep in mind, like as I'm reading or talking, I might not catch them, but if you send them to everyone, Lindsay can catch them in the chat too while I'm talking. So the question was, do we have to state that X is equal to 2A and Y is equal to 2B? Or can we say, therefore, X plus Y is equal to 2A plus 2B? So I assume that this came in reference to what happened up here. And I do think that is a necessary step there. That's a good question. Like the question is, can we start here and then just jump right to this? And I do think that this is really important since this was the original hypothesis that they're even, that it is useful to show what does that tell us? And that's how we got here. So I do think that that's a good step to show there. Doesn't take too much, and it might clear up some confusion for the reader. I certainly agree that some people might not need that line and might be able to make that jump, but let's just save them the effort and just tell them where that came from. Any other questions? And I just want to say, like, when you're avoidable, you don't really want to use cases unless you have to. And so if you kind of reflect back on one of these proofs over here, yeah, I don't think any of these actually could have thought about some cases, but I'll just say there may be some situations where your initial reaction might be to use cases, and then you look at the proof for each of the cases and you see, you know what, like these proofs are all identical. Do I really need to do these cases? The answer would probably be no. So just keep that in mind. Sometimes it's great, sometimes it's not, and that's part of the difficulty of proof writing, is to kind of think about what proof technique or what proof constructs do I need in order to prove this.
How would you do that one without cases?
I don't
if you
think you
didn't-
could. Yeah,
Yeah, because can't think of a way you could do that
That's
without
right.
cases.
and I think like when you're in that situation, that's when you use cases. When you're in the situation where like, I see that I could have done that without cases, then it's going to be a better proof to do it without the cases. I'm not saying it's wrong to do it with the cases, but I would say if we're grading like on the Olympic scale out of 10, if you use cases when you don't need them, that's like an 8 out of 10. Not saying that's how I would grade it on an exam, but like on a terms of like how sophisticated is your proof, it would knock it down a little bit. Okay, so I think this is a good time for you guys to try and get some work in. We're certainly not going to get through all of these. So I just want to kind of pick out a couple that I think might illustrate some different parts of proofs, and maybe have different groups work on different things. So I'm going to just create some breakout rooms first of all. Don't jump into them just yet. I'm just kind of curious to see how many we have first. Okay, so we're gonna have a couple of rooms of so we're at 4 different rooms of about 3 people in a room. So let's see, we did this one, did this one. So we're here, right? So I'm gonna say there is one group, please hang out here for a second. So the first group is a room with Giselle and Kaden and Christina and Nicole. So if you guys want to start with proof number 5, that's great. And, you know, and then if you finish that one and you want to move on to some of the others, that's great. But I would like that room to start with number 5. I've got a second room, which is Carmel and Casey and Ken. How about you guys can take number 6, and then we've got Diane and Keenan and Zoe. We'll skip 7. We'll give you guys number 8. And then in room number 4 is Bill and Jonathan and Mitchell. If you guys want to take the 9th one, that's great. We'll skip 7. So I would say, you know, focus on the one that you were assigned first. And if you wrap that up, then start to think about 5, 6, 8, 9, because that's what your classmates will be thinking about. So let's shoot for maybe about 10 minutes of discussion on these. I'll say it would be really, really nice if you guys can use like a screen share while you're talking to each other, so that you can kind of collaborate and write up a proof together. That way, when Lindsay and I go into the rooms, we'll kind of see what you guys have been talking about. Any questions? All right, then we'll see you in the breakout rooms. Thanks. Okay, so for the group that worked on this one, how did it go?
I think it went pretty well.
Yeah, I think we got it.
Yeah.
Yeah.
So you guys want to walk me through it?
I can do it if no one else wants to.
Sure. Thank you, Giselle.
Yeah, we started with given, or X is an even integer.
So, okay. So cases, is that the idea here?
Yeah, sorry. Yeah, case 1, X is even, and then so like thus X is equal to 2A, where A is an integer. Yeah, sorry, suppose X. My lingo is bad.
No, you got it. Okay, so we'll start here. If X is even,
Suppose X is even, thus X equals 2A, where A is an even, or where A is an integer.
mhm.
Um, and then I don't know the lingo. So X squared equals 2A squared.
Mhm. Yeah, and so I think this came up with some of the rooms. Like, I think one thing that's safe is like we all know how to do algebra. Your classmates can do algebra, so we don't need to like explain the details. Certainly, you're welcome to say x times x is 2a times 2a is 4a squared. We've all got that down. So yeah, so this is totally fine to jump right to that.
Oh, okay.
Yep.
Yeah, so this gives X squared equals 4A squared,
Mhm.
which you can rewrite, which equal 4A squared equals 2 parentheses 2A squared. And then we could state that 2A squared is equal to, is an integer, is equal to integer D.
Yep.
Or thus you end up with 2 times an integer, which is the definition of an even number, an even integer. Therefore, if X is even, then X squared will be even.
Yep. Good. Yeah, so that handles the case where, okay, if X is even, then we've shown that X squared also is even. Great. And so then there's a second case, which would be suppose that X is odd. Yes. And then what do you guys do for this one?
Yes, we did. So suppose X is odd, then X is equal to 2A plus 1, where A is an even integer. Is it okay that we use the same
Yeah,
letter? Okay.
that's okay. It's kind of like each of these cases you can think as like clearing the memory of your computer, and we've now emptied out whatever A was, and we can redefine A. Yeah, I think if you were like defining A as two different things within the same case, you're going to have some problems. But down here, it's fine. If you're uncomfortable, then we've got plenty of letters. But yeah, that's totally fine.
Okay.
So then we have that X is equal to 2A plus 1 for a some integer.
So this so this gives X squared is equal to, and then I'll just go immediately to like the factorial. X squared equals 4A squared plus 4A plus 1, which you can factor equals 2 parentheses 2A squared plus 2A and parentheses plus 1. And then we just stated that let 2A squared plus 2A equal C, where C is an integer. Therefore, 2C plus 1 is the definition of an odd integer. And therefore, X squared, if X is odd, X squared is odd.
Yep. Looks good. And I don't think that you could really do this without doing cases because they're different. These two things were done quite differently. Yeah. But the nice thing is when we're talking about parity, there's only 2 options. So it's not like we need to have like 8 cases. It's just if it's even, if it's odd. Any questions? I'll just say, like, it is fair game if you wanted to. Certainly, I'm glad you didn't, because it's good practice. But we did prove this together last time. So you could say case 2, see question 2 is fine. I just want to say, like, you're able to refer to things that we've proven previously. If you're not sure, then it's certainly safer just to go through the proof again. Great. Any other questions from others in the class? Okay, then in 6, let's see. See if this will work. Did not. Okay. So the group that was working on 6, what was the claim that we're trying to prove here? Sorry.
It's x and let x and y be integers for all x cubed minus x is even.
Say the second part again, Kenneth.
Yeah. For all x cubed. Well, for all x comma x cubed minus x is even.
Okay.
Yep.
Yeah, and so again, one kind of subtle thing here is that these for all statements are conditional statements, right? So you can think about writing this as if x, again, I don't know why there's a y in this statement. I probably was just copying and pasting, but we don't have a y, right? So if x is an integer, okay, that's another way of writing out the statement as a conditional statement, which might help if you're trying to do direct proof. Yeah. Okay, so did you guys make progress with this one?
Yeah. So for this one, I think we concluded that this was also a case situation because we want to prove it for even and odds. So for the first one, we said case 1, x is even. And then suppose x is even.
Yeah, I'm trying to listen. I'm following you, I think. So case
Oh, okay.
1 was
Yeah.
suppose x is even.
Yep. Suppose x is even. Then x is equal to 2a, where a is an element of all integers. Yep. And then this means that x cubed minus x is equal to 2a cubed minus 2a.
Was 2a cubed minus.
Yeah, 2a to the power of, yep, minus 2a, which is equal to 8a cubed minus 2a. And then equal to 2 parentheses, oh, just factor out of 2, yeah.
Nope, that's not how you factor.
Equal to 2c. I just did a long series of equal.
Yeah.
Yeah. And then where c is an element of all integers, therefore x cubed minus x is even. Yep.
Any questions or comments about that case from anybody else? You guys think that looks okay? All right. Let's see. I see I added the page in the wrong spot. Okay, so that was the first case. And then what was the next case that you'd want to consider?
The other case would be x is odd.
Yeah, and so, yeah,
Okay, and then I started with suppose x is odd,
mhm.
then x equals 2a plus 1, where a is element of all integers.
This is great. Yeah. And so you guys are being very good about this. And again, yeah, definitely be very careful about any time you introduce something over here that you don't just skip over this detail, right? By saying, what is this object A? Yeah. Okay.
I said this means that x cubed minus x equals 8a cubed plus 12a squared plus 6a
Okay.
is equal to, and then just factor out a 2.
How'd I do?
Yep. And then I set that equal to 2d. Well, I do have a quick question. Can I also use, can I do another 2c situation, or do I have to do the next alphabet letter?
Yeah, either way, it's fine. I think,
Okay.
you know, like each time you start a new case, yeah, we're kind of purging the previous. However, we've defined things previously, and you can recycle them if you want. If you're not comfortable, then yeah, just use another letter. That's fine.
Okay, yeah. I just said 2d, where d is an element of all integers. And then therefore x cubed minus x is even. And then the cool red box.
Yes. Oh, not also, but. Yeah, and I think, you know, now that we're doing these cases, which is kind of not that surprising with even and odd things, this is good. No, I don't see any problem with this. You might just want to stop and think to yourself, like, did I really need to do two different cases? And I think here, yeah, we did. Like these followed differently, so there was no way to do them in one shot. Okay, so we have just a couple more minutes left here. So I didn't, sorry, I ran out of time to get to all of the groups. But maybe something that's a little bit different would be the last one that I asked you guys to think about, which was number 9. And I know that the group that was working with that was doing a pretty good job. So I just want to talk about this one because it introduces a couple of new things, which is like, what does it mean to be linear and quadratic, which again, you know, probably we've come across those definitions in a previous class. So this one is saying if functions f and g So this was a little different, right? We don't have even and odd things here. And so for the group that was working on this, how did you start this off? If you don't mind sharing that.
We stated that any function can be function f of x can be written as mx plus b, and any function g of x can be written as nx plus c.
Yeah, thank you. So here we're going to do direct proof. So we're going to suppose that, I guess I can say that, these are both linear So it follows pretty similar to the even and odd stuff. So we just say, like, by definition, what does that mean? Okay, and it just means we can write it as some real number times the variable plus some other real number. So similar idea here, but these values in the formula for these functions, right? They don't have to be integer valued functions. They could just be any real number. And then other than that, right? It's pretty much just an algebra problem at that point. So, you know, what we'd like to show is that the product is quadratic. So then let's consider the product. And I realize we're just about at a time here. But multiplying these together, what would we get? Was it mn x squared plus
mxc plus nxb plus bc.
Yeah, I'm gonna write it like this. Sorry, I ran out of space. And what's left is like BC, is that right? Which by definition is quadratic, right?
I think that was the only question we had. Can we take the fact that a function has a squared as an axiom, or do we need to prove a global minimum or maximum?
Yeah, no, the definition, I'm just sorry if I'm making you dizzy scrolling way back over here, is just saying, what does it mean to be quadratic? It means that it has a degree 2. And so I think actually one detail that should be left out, that I did leave out over here, right? We do need to say that, okay, f and g, these are linear functions, so we can't have m or n be 0, or else it would be a constant function, right? So we just need to make that specification. And that's important because then over here, if m and n are not equal to 0, both not equal to 0, then the product m times n is not going to be 0. And then so yeah, so in order, what do we need to show to claim that something is quadratic? We need to show that it's a polynomial that has degree 2. And so that means that the coefficient in front of the second term, the squared term, shouldn't be 0.
Do you need to add anything there about like when you multiply those two linear functions together, the mc plus nb is a real number and the b times c is a real number? Or is that just kind of, if you already have real numbers up there, define mb and c, that the product or sum is going to be real?
Yeah, I think that would be fine, not I mean, it doesn't hurt to comment on that. If you leave that part out, that's not really, I think what we're really focusing on here is like, we're really concerned, I just erased it instead of highlighted it. We're really concerned about this term right here. Yeah. And so, yeah, this is what we really care about. The fact that these are real numbers, I think that's, it's probably pretty clear, and also not really the focus of this, but yeah, it's fine to say, MC plus NB and BC are all real numbers. I don't think that's necessary though, no.
Okay, all right.
Okay, I'm sorry. So I'll stop here. We didn't start talking about worksheet 5 at all. That's kind of what the video and the reading quiz are going to be about next time. I think that a lot of some of that stuff you're probably familiar with. So we'll kind of just pick up, seeing if you have any questions about set notation, and then we'll start incorporating sets into our proofs using direct proof. Okay, well, thanks everybody. In the meantime, if you have any questions about the homework, you can reach out to Lindsay or myself. That is due Thursday evening. You should be able to go through all of the problems now. There's nothing that we're going to talk about on Wednesday that you would need for the homework that's due Thursday. All right, well, have a nice afternoon, everyone, and I'll see you on Wednesday.
Thank you.